Hello again. We are ready for the final section of Chapter 6, and that is talking about the central limit theorem. The key concept here is that any distribution, the distribution of the sample means, and we talked about sample means in the previous section, approaches the normal distribution, and as the sample size increases, that distribution becomes more and closer to the normal distribution. The procedure is really foundational for estimating population parameters, and when we move on in Chapter 8 on hypothesis testing. The random variable that we use has a distribution which may or may not be normal, but the mean and the standard deviation, a simple sample of all n that are selected from the population, they must have all the same chance of being selected. So, the distribution of the sample means will, as the sample in size increases, will approach that normal distribution. The mean of the sample means is the population mean, and the standard deviation of all sample means is the standard deviation divided by the square root of the number of items in each of those samples. So these are just some practical rules that we use in statistics. For samples that have 30 or larger, the distribution of the sample means can be approximated by using that normal distribution. Again, the higher the number, the closer it comes to the normal distribution. And here's the interesting part, is that if the original population, regardless of how many are in there, it could be 4, 5, if that normal original population is normally distributed, then for any sample size, the sample means will be normally distributed. So if you start with a normal distribution, your sample means are going to create a normal distribution. So here's some notation. The mean of the sample means, the standard deviation of sample means, and many times this is called the standard error. So here's what we're referring to. This is our distribution. Notice that this distribution is a normal distribution to start. So we know that the sample means are going to be normally distributed. And then we can see each one is a different, and you can see the distribution here. And again, a 50. And we can see that nice normal distribution. Even when in the beginning that distribution is uniform, notice that we got to an n of 10. At an n of 10, it's not great, but it's getting better towards that normal distribution. But look at n of 50. Wow, getting to have a normal distribution for sure. Even if we have a U shape to begin with. Now we're moving again, n of 10. With an n of 50, we have a very normal distribution. So here's an example to do. Suppose an elevator has a maximum capacity of 16 passengers with a total weight of 2,500. So many times you get on an elevator and you'll see those signs, maximum capacity, how many passengers, and it also gives a total weight. Assuming a worst case scenario in which the passengers were all male, what are the chances that the elevator is overloaded? Well, let's make some assumptions here. Assume that the male weighs have a normal distribution with a mean of 182.9 pounds and a standard deviation of 40.8. 2.8 pounds. Now we need to find the probability that if I randomly select one male, that he has a weight greater than 156.25. So here we go. It's going to go back to us drawing out that curve so we can see what's happening. And of course, we will take a look at what we can do the calculations on the calculator. So here we go. Let's get a pen here. Let's draw what's happening. Normally distributed weights. It says that the male has a mean weight of 182.9, so 182.9. And the standard deviation is 40.8 pounds. Now, it says I want to know what is the probability that one randomly selected male has a weight greater than 156.25 pounds. The reason we're using 156.25 pounds is based upon this elevator rating. The elevator is rated for a capacity of 16 passengers with a total weight of 2,500 pounds. Well, if that were the case, those 16 passengers would have to have a mean weight of 156 and a quarter. So if you take 2,500 and divide by 16, you're going to get 156.25. So that's what we want to check. Well, if I look at my distribution here, I can quickly see that 156 and a quarter is going to be down lower than our mean. And I'm just going to randomly pick someplace, 156.25. So I want to know greater than. So the part that I'm looking for is this. Of course, we can find our z-score and look at the table. There's so many things that we could try to do, but we know how to do this on our calculator. This is a normal distribution. Okay, my lower end is not negative 1 e to the 99. Our lower end is 156.25. Our upper end is going to be way out here to the very end of the tail, so I'm going to put 99999. The mu is 182.9, and my standard deviation is 40.8. Those of you on that calculator without this screen, again, you're going to pick the normal distribution. You're going to put comma. You're going to put 156.5, comma, 9999999, comma, 182.9, comma, 40.8, and then close your parenthesis. We're going down to paste, enter, and we're going to get that it's 0.743 rounded to. So again, that's an area. That is an area. So being an area, I'm going to write that in 4 places. So 7432. 0.7432. So we like to think of percent, 74.32% of a chance that I'm going to have one individual man selected that's going to be greater than the average that they calculated the weight, safe weight for on this elevator. I think it's a pretty good probability, almost 75% chance that it's going to be a male that weighs more than that. So that's what we've been doing in the past. That was SciThink section 3. Now part B comes the central limit part. Find the probability that a sample a sample of 16 males have a mean weight greater than 156.25, which puts the total weight at 2,500 pounds, exceeding that maximum capacity of that elevator. So the thing that we have to do is we know that the mean is going to stay the same of 182.9, but what's different is a sample standard deviation is equal to the standard deviation divided by the square root of the number of our people in our sample, n. So of course our standard deviation is 40.8, and our number, I should have put in there first, sorry, anxious to fill in the blanks, and square root of 16. That was how many was our sample. So I can quickly figure that out, and it's going to be just over 4, but we'll get our calculator here, and we'll do 40.8 divided by the square root of 16, which obviously is 4, and that's going to give me 10.2. So that is my sample of 40 and what is going to be greater. Finding that sample and what is the chances that it will have a mean weight greater than 156.25. So again, we're going to go ahead and draw that normal curve, sketching that example. Our mean is 182.9. Our new standard deviation is 10.2. And we still want to know 156.25. So let's bring up our calculator. We're going to go into our distribution again. We're going to have the same with everything except for the standard deviation, and we're going to change that to 10.2. Enter. And wow, didn't that change? So 0.9955. 0.9955. So that means there is a 99.55% chance that my sample of 16 men will have a mean greater than 156.25. That's a pretty big chance. Many of you are sure are probably too young to remember, but we had ferry boats that had the wrong, I believe one out of the Baltimore Harbor that sank because the load, weight load, and the number of passengers were very different, just like this situation. So let's do a couple more here before we end our video. Loading M&M packages. M&M candies have a mean weight of 0.8565 grams and a standard deviation of 0.0518 grams. There is a data set that is with your textbook, but from that it's data set number 20. It contained 465 M&Ms, and the package label stated that the net weight was 396.9 grams. If every package has 465 candies, the mean weight of the candies would exceed the 3 96.9 divided by 465, it would exceed the 85.65 grams for the net contents. So if one M&M candy is randomly selected, find the probability that it weighs more than 0.8535. Again, we're going to start with that picture. So here we have that plain candies have a 0.8565 grams and a standard deviation of 0.0518. So now I want to know if one M&M plain candy is randomly selected, find the probability that it weighs more than 8535 grams. Well, here's my mean of 8565. So I know this is smaller, so it's going to be on the left-hand side, 8535. And I want to know when it's greater. So again, I want to know the area under the curve here. So let's go to our calculator for our distribution, normal distribution. The lower end is going to be 0.8535. The upper end is going to be 9999999. Mu is 0.8565. And the standard deviation is 0.0518. And again, if you've got that calculator at home without the screen, you're going to put parenthesis 0.8535, comma, 99999, comma, put the mean 0.8565, and the standard deviation 0.0518. And enter, and we find that this is going to be 5231. So that means there is a 52.31% probability that it weighs more than 0.8535 grams. If 465 M&M candies were randomly selected, find the probability that their mean weight is at least 8535. So now I'm not choosing one, I'm choosing 465. So 465 instead of 1. So remember how my standard deviation changes. The standard deviation for the sample here, I'm going to take 0.0518 and I'm going to divide that by the square root of the sample size, which happens to be 465. Yes. So bring that calculator over. 0.0518 0.02, and that's as much as I saw. I'll have to get my calculator back. 4. So there's my standard deviation. So I want to rerun this calculation using the new standard deviation with a sample size of 465 M&Ms. So we'll go to our distribution again. And this time I'm going to change that standard deviation to 0.0024. And I'm going to get that that area would then be the probability 89, I got 89, I remember that, 89.44, 89.44, or 89.44%. And that means that I've got a real good probability that those M&Ms are all going to weigh a little more than 0.8535. And so is it probably right? Yeah, they're probably right. That's going to be a good possibility that they are, considering that it would be a probability of 89% for any sample to come in weighing more than 0.8535 grams. That concludes all of Chapter 6.